We are asked to find the joint PMF of x and y and n, where x and y are i.i.d. geometrical, and n is the sum of these two. Okay, so the joint PMF is the probability of x, y, n. And here, one way to think about this is that we at first are not given the distribution of n. So if we can write this PMF in terms of x and y's, we then can use the fact that we're given the geometrical PMFs, and because they're i.i.d, we can just multiply them together. So let's factorize this by writing x. Can we condition on x or y? It doesn't matter. So let's start by conditioning on y. And then we can condition this further by writing n conditional on x, y, x condition y, because of the fact that we have already conditioned y, we have to condition here. But now because x and y are independent, we can write this as p of x. So this PMF can now be written as and another fact here before I go on is that once we condition on x and y, we know what n is. It will become deterministic. So if we know x and y, this will become 1. So it's always probability 1. Whatever x and y is will determine n with probability 100%. So this we can write as 1 times p of x times p of y. And we know what the geometrical distribution PMF looks like, so we can just multiply them together. So I'm skipping now the 1 here and just write, and the geometrical distribution means the number of failures until the first success. So this will be like so. So the first success occurs with probability p, and all the failures occur x times these, and they are all independent, these failures. And the same thing with y minus p. So the whole PMF now is x plus y p squared. That's the PMF of the joint distribution. In B, we're now asked to find the joint PMF of x and n. So a natural way is to sum over, so we marginalize out y by looking at the joint distribution of x, y, and n. Now, this will this is basically the way we by following the definition will be going about it. However, as you will see, there is actually a much easier way to think about this problem, because so let me just write this out to show you what I mean, which is that we now do the following. Just factorize out y, like so. We sum over all the y's here, so y will be going from its support up to n. Now, as you're seeing here, we can write this out, but then we're sort of stuck with this, which we can keep on factorizing it and arrive to the correct distribution. But a much easier way to think about this is to just take x and n, the joint of x of n, and then condition on x by the law of total probability. And this way we wouldn't have to use the sum at all. And n, we know, is the sum of y and x, and so we can write this as so it's the sum of x and y, but we have conditioned on x, and it should be very clear that we have conditioned on a little x here. So I'm going to make some room to write little x just to clarify that it is at a level of x. So I can write little x instead of the random variable x, and this is equal to n. And to clarify where the n is coming from, it's because we're looking at the random variable n equal at little n. Conditioning now, little x, like so. We can now subtract off a little x here, so we'll end up having n minus x, and I can remove, because I'm conditioning on x, I can basically just treat it as unconditional, but because we have written in x here, it's implicit that we're at the level of that we're already conditioning. And here now we're back in the distribution of the PMF of y, and this is the PMF of x, and so we have 1 minus p n minus x, and times p, and 1 minus p x p. And so we add these together, we end up with 1 minus p n p squared, because the x's here cancel when we add it together. So that gives us the PMF of x, the joint of x and n. Now notice that we are sort of implicitly given the PMF of n, but which will be very valuable now in the second the third question. So let's head on to look at the third one here. So we are asked to find the conditional PMF of x given n and little x, and then just give a simple description of the words that this result mean. All right, so C, we are now targeting the conditional, so we're going to write down my base rule, n equal little n, and here we have the joint of this, and we already know the joint because we just calculated it from here. So we can basically copy this like that, and then we have to find the marginal of n at little n. So this marginal has to it sort of follows from further marginalization of this term here. So what is that? So let's think about that problem. So this, I'm going to continue here, n is the same by relying on the law of total probability. we now sum over all values of x, and that, copy this term here, because that's the joint, so we're summing over that one like so. But the tricky part is really the support. I mean, the geometric goes from x to arbitrarily large integers, but here, because we are conditioning on n, little n, x cannot be more than, so x has to be less than or equal to n. So writing out that support, so we have x equal 0n, 1 minus p and p squared, and taking out the p squared like that. And notice that we can actually also take out this term here. Even if this n is actually x plus y, this n index is now treated as an index in its own right. So the sum doesn't depend on x. Sorry, the sum depends on x, but not n. So we can actually take that out too, and we end up having n plus 1 terms, right? We start at 0, so we have n plus 1 terms. So this whole thing simplifies to n times n plus 1. And so just putting it in here, we have, let's copy this, duplicate like so. We'll take this term like that, and this whole thing now, these terms cancel, these terms cancel, so we end up with n plus 1. And this is, in terms of words, this is saying that, I mean, basically n is negative binomial. And the negative binomial, so where the geometric distribution counts the number of failures until the first success, negative binomial counts the all the failures up until one or more successes. Yeah, so we have several failures until we have 1 or 2 successes. And in this term, in this problem, we have n being having 2 successes. So if we're going to visualize what this means, we can think about the meaning of this is that you have 0 up to n number of failures, so this is large N, and then we have to have, if those are all failures, n plus 1 first successes. So the first success occurs after all those failures. That this is the simple geometric, but the second success has to at earliest occur at n plus 2. So what we have, what this term here is saying is that it's equally likely that the first success, all failures occur in this domain here. So that's the interpretation of this result.